as well. How we want to make sure all the sample at the end turn out in the right form, okay, in the right form, and then this, let's say for a small wire like this, and the end we run with the suitable instrumentation. All right. So that is one of the challenges. All right. To make sure that our sample is ready for the next step, which is analysis. And then another challenges that always we encounter is about the trace analysis. Why? Because normally our targeted analyte at a very low concentration, at a very low concentration, and also we have a very complex matrices. Okay, so how we want to overcome all these issues? All right, because both challenges, concentration, which is the too low concentration, and the complex matrices, which is maybe we have a very complex like a soil or fish and so on, will be produce a very poor sensitivity method. So how we want to overcome? So the best solutions to overcome all this problem in the analytical chemist, we always go for the sample preparation. Sample preparation is one of the steps before the analysis. So let's say that I take the samples and then I want to go to the lab and to run the samples. But before I want to run with a particular sample, particular instrument, I should make sure that sample undergo this process we call is a sample preparations. So under these sample preparation techniques, we will ensure that our samples, we remove all the matrices, which is one of the main obstacle, and then we change the sample in the right form, and then we increase the concentration, then the sample can be easily detected. How we have a lot of techniques, but today I would like to focus on the one technique only, which is solid phase extraction techniques. So what is a solid phase extraction technique? It's a very simple technique. We have a solid phase. We either we put in the cartridge or whatever. All right. So our interest, the targeted analyte, we interact with this particular solid phase. All right. Then we do the interaction. So the interaction is depend is what type of solid phase that we use it. You want to use the long chain, or you want to use the aromatic, or you want to use a cation or anion, is up to us. It depends on what type of the targeted analyte that we want to attach to this particular solid phase. So the selection of this solid phase is very important. All right. So I give the examples here. This is one of the common sample solid phase that have been used in suppression study. So for those that normally use HPLC, okay, for the suppression, they always know this material, which is we call as a C18. This C18 is widely used because they can do some hydrophobic interaction, as well they can do a van der Waals interaction and so on. All right. So normally in our lab, we always do a design the material, design the solid phase and so on. But how we want to, at the end, when we do all these things, finally one day I thinking that why we keep designing, and because sometimes we use a lot of chemicals, and some of the chemical maybe is highly toxic and so on. So that's why at the end, we start to turn our material, which use natural products, okay? The material that we can easily get in our kitchens, all right? So normally, we will call it an edible natural product that we can easily access in our kitchen, all right? So some of them at the end will turn to become a waste, like a orange peel, potato peel, the tea waste. We always throw at the garbage at the end, all right? But for me, don't waste your waste, all right? Don't waste your waste. Why? Because waste is a natural resources in the wrong place. Change the context and you have usable products, all right? So I love these quotes because from these codes, I managed to do a lot of things and apply in analytical chemistry. All right. So maybe some of you think that how this edible natural product, maybe some of them is a waste. I relate with the sample preparation, as I mentioned just now. And then at the end, when we use all these biomaterials, of course, at the end, we can turn our instrument, our technique can categorize as a green analytical chemistry. Okay, how we want to relate all these things. All right, it's a very simple because chemistry is everywhere. Chemistry is everywhere, all right? Even in our kitchen, there is a lot of chemistry, okay? When you eat your mangosteen peel, okay, you remove it, all right? You can know that a lot of things that the aromatic compound inside here, all right? Same goes with the prawn shells, all right? We have we can have a ketene, which is we can convert to ketosine. And then if let's say that garlic peel, okay, there is a lot of sulfur group from the L-cysteine. So all these things will make us we can explore a lot, because in our natural product, there is a lot of hidden potential that we can explore it. So this is our first part, okay, the first journey when we use our waste in our kitchen and turn it as one of the material that can be used in analytical chemistry, okay? So one of that is we use the waste cooking oil. Waste cooking oil, we use it to turn that the magnetic nanoparticle as a super hydrophobic. This super hydrophobic material will be used as to trap the polysaccharide aromatic hydrocarbon in service sludge and landfill leachates. All right. So this is why we choose the polysaccharide aromatic carbon, because the character is a toxic, mutagenic, and carcinogenic. All right. So based on this structure, for the chemists, all of you will know that this is a lithophilic character. When this is a lithophilic character, we need a hydrophobic absorbent. All right. So hydrophobic solid phase is needed for this type of category. Therefore, we would like to introduce the waste cooking oil, all right, to the magnetic nanoparticle, waste to chemistry concept. Maybe some of you will ask why I choose waste cooking oil. Because waste cooking oil have a source of the fatty acid. Okay, fatty acid, for example, palm fatty acid consists of the palmitic acid and oleic acid, as well as linoleic acid. So these R, which is we attach to the magnetic nanoparticle, at the end will turn to form as a very long chain and turn to become a hydrophobic material. So we managed to prove that. Okay, we managed to prove that this material, this material that we attach with the waste cooking oil, to form as a very super hydrophobic material through this contact angle analysis. Okay, so based on this, we say that this is super hydrophobic material that can able to capture the polysaccharide aromatic hydrocarbon. So the synthesis is very simple, all right? And the process of the sample preparation, so this is one whole the process of the sample preparation, because we attach to the magnetic nanoparticles, so we can use a very simple magnet to do the separation of the magnetic with the solutions. At the end, when we get this, we get the material, the solution, we run with the HPLC and we get very nice spectrum. All right, so we prove that. We prove that through the analytical performance data. Okay, we do a lot of method validation to confirm that this method is suitable. All right, and then we test this method in the leachate and also sludge as well, and the result shows that it's good performance. At the end, we managed to get. We can show that from this chromatogram. This is for information is from the leachate samples. So you can see, even though it's a leachate samples, when we pass through with our material, they can produce a very nice peak. Very nice peak. There is no interference in that particular region that we want to detect. All right. So when we start with the polysaccharide aromatic carbon, we can see that very nice chromatogram can be get from this material. So we continue this method. We continue with the same approach with the base cooking oil. We continue, but we replace it instead of magnetic nanoparticle. This time we use again with the waste. We use the mangosteen peel. Why mangosteen peel? Because I love with this aromatic ring, and this aromatic ring able to attach with the polysaccharide aromatic hydrocarbon. All right. So we do a
Excuse me, Dr. Sarifa, you have 2 minutes left.
All right. I will finish it. Try my best. All right. So this material at the end we embedded and apply in the as a polysaccharide to trap the polysaccharide aromatic carbon. Okay, we managed to validate it. All right. And the third one is we use the spent tea leaf. Okay, spent tea leaf we use to trap again with the polysaccharide aromatic carbon. I speed up a bit. We use spent tea leaf, we boil it, all right? And when we study the interaction, we managed to get a very nice materials, this material to absorb the polysaccharide aromatic carbon. This is a simple method to fabricate our sample techniques. All right, we use a lot of type of samples at the end. For example, rice, apples, and juice, and we validate it. And then finally, we managed to apply in some samples can be detected of the polysaccharide aromatic carbon. Okay, this is from the water samples. All right. So again, we can prove it through the chromatogram. It's a very clean samples after we run with our spent tea leaf. All right. So this is last part. Okay. Even though there is during COVID-19, we close our lab. We still want to explore what we can have in at home. So we do testing experiment lab at home with monitor our food spoilage.
I'm sorry, Miss, your speaker is mute.
All right, sorry.
Yes.
All right. Yes. Okay, I'm sorry. I'm not sure that which part, but can I go to the conclusion, Dr. Yuma? Or you want?
Yes. Okay. Thank you very much for your inspiring presentation. We invite participant to ask one question to Dr. Sarifa.
All right. So can I stop this presentation? Can I?
Yes. Can I ask one question to Dr. Sarifa?
Yes, sure.
Okay. Your material is suitable to separate. Is this material can use as quantitative, can use to determine quantitative parameter?
Yeah.
As resin, cationic resin, anionic resin?
Yeah. All our material that we use, as mentioned just now, waste cooking oil, spent tea leaf, all we use for quantify the polysaccharide aromatic carbon. So we can detect the samples in the, let's say I use water sample, I want to detect polysaccharide aromatic carbon. I can use this material to detect this one. Okay, we use a simple sample preparation just now.
Okay, thank you very much. There are no questions, okay, from the participant. Okay, thank you for your interesting presentation today. We will follow the next presentation. Okay, thank you very much. We invite Associate Professor Dr. Ahmad Taufik as the second invited speaker to present the presentation. Dr. Taufik, the time is yours.
Okay, thank you very much, Dr. Irma Kartika, for giving me an opportunity to present our recent works. Now we are going to discuss about our recent works entitled Magnetic Fluid or Ferrofluid fabricated from Indonesian natural sand for energy harvesting agent. So here in this work, we have already synthesized the magnetic fluid or ferrofluid in various ways. And we have also developed various methods in order to increase the performance of this ferrofluid. Before we go to what is the ferrofluids, I would like to present our recent updates, especially in the last 10 years. Actually, we started our works, especially experimental for fabrication, for synthesizing, and also for characterization. We started this work from 2006 until 2016. It is about 10 years. We have already developed various methods. So we have already fabricated stable and also flexible ferrofluid formulation. After about 10 years, we developed various methods to get stable and also flexible ferrofluid with various ways, with various routes. Then we continue to investigate the nanostructural and also magnetic properties, including optical properties, some physical, some chemical, and also some biological properties of the ferrofluid have been investigated properly. Here, we would like to show that in the atomic scale, we investigated the hierarchical nanostructure in 3 dimensions using small angle X-ray scattering and also using small angle neutron scattering. Why we use this method? Because ferrofluid consisted of filler with magnetic particle in nanometric size and also covered by some surfactant dispersed in various liquid carrier. Without small angle neutron scattering, without neutron, it is very difficult to study the magnetic properties because ferrofluid can interact not only with the particle or electron, but also can interact with the neutron. This is the most powerful properties why we use ferrofluid. And also we use quartz magnetometer to investigate the deeply properties of magnetization. And then we also develop some sensor application, especially for temperature sensor and also for magnetic sensor. So we have already got good or excellent properties of this sensor. It is about 2 years ago, we started for biomedical application for antifungal or antibacterial agent for drug delivery system, fibrotic, as well as for anti-cancer agent. Now we also develop our ferrofluid system for energy harvester. This is the new one in our project because many researchers just only focus, for example, for CIGS, and also for solar cell, and also for another thing. But we would like to investigate the ferrofluid can be used in order to get energy harvesting agent. So this is the new one in our project. Our previous in here, we have already published several article in various publication journal, for example, in Springer and also in Elsevier in other ones, in another one. This is 2020, and also this is this year, and also for corresponding, and also for first author, and this is our student paper from undergraduate and also master student. So we have several student, undergraduate, and also master student can produce with their first name. This is Q1 with a high impact factor about 8, and this one also with a high impact factor when Web of Science. So why it is important to investigate the ferrofluid for energy harvesting agent? We know that in atomic scale, in crystal structure, the spinel structure, especially for magnetic nanoparticle, the irons can be placed in octahedral or octahedral position with certain or with specific magnetic spin. So in order to increase the performance, we can change, we can substitute with other element, with other metal. For example, in here, we use titanium and also chromium with certain ion. So we use a natural sand from Indonesian natural sand. We know that in Indonesia, we have many places with high iron sand content with high purity. So we utilize this natural sand by chemical process. For example, in this work, we use chloric acid in order to get iron, titanium, and also chromium chloride, and also we use base solution to make a nanoparticle. But the most important thing here, without surfactant, without liquid carrier, it is very impossible for us to get good flexible ferrofluid. So we use not only single surfactant to get very stable ferrofluid, we also use the double surfactant in order to get high stable ferrofluid. So in the application, it can higher performance than others. Okay, so the next one here, the key concept why we use magnetic fluid or ferrofluid for energy harvesting. We know that energy harvesting here, based on our ferrofluid, we use an external magnetic field, and we can use in small magnetic field in here. For what? For trigger or also slowing the movement. In order to change, in order to produce magnetic flux, that's change in the time. Now, this movement will induce electric motion and also can produce by the force in this contact electric or magnetic force in the coil. So when the magnetic fluid is triggered by this force, so electric current will convert external vibration for what? To produce electrical energy. So in our work, to produce optimum slowing movement, our magnetic fluid should be in steady state. Without steady state condition, it is very impossible to get a good energy harvesting agent. The second one, in our simple electrical measurement here, we use this simple spring and place the free fluid in the coil, and then by some mechanical energy, some force, so we can make a sloshing movement in here by electric theoretical, very basic or fundamental physics here. Yeah? When our ferrofluid in here is externally stimulated by magnetic or electric force, so we can combine with the mechanical motion to produce fluid change with the time. This producing flux change in the time, we can induce electromotive force. So by this electromotive force, we can convert into electrical energy. This is the simple concept why we use magnetic fluid. This is our X-ray diffraction data. Based on this data, we can see that doping process, substitution process from titanium and also from chromium ion have been successfully inserted into Fe3O4 without any impurities, without any anedopics. So because titanium and also chromium have different ionic radii, have different magnetic moment, so they will increase the magnetic and also stabilization of the ferrofluid. We can see in this figure, in this crystal structure, in the octahedral position and also in the trihedral position, surrounded by 6 oxygen atom, and also for tetrahedral, the metal ion surrounded by 4 oxygen atom, will makes good orientation to get more stabilization, to get more magnetic character, especially for saturation magnetization. For morphology obtained by scanning electron microscopy investigation, we can see in here that iron, oxygen, titanium, and also chromium, all of them have been successfully inserted in the system of the ferrofluid without any impurities. We know that our main precursor here, we use natural iron sand. So from this figure, we can see clearly that all the sample, all the material that we produce here have been in nanometric size. We can convert here by some fitting or some calculation. That's, for example, for Fe3O4, this is about 30 nanometers. And the other ones, for example, for FF5 with the chromium ferrite oxide, this is also very small in nanometric size. The next one in here, we can see the magnetic properties. Without doping with titanium and without doping with chromium, we can see in here, in the left one, the magnetization in here, we can fit by using Langevin function. Here, this is excellent superparamagnetic material. Actually, ferrite is very magnetic. But when we produce the material in nanometric size, especially below 10 nanometers, we can produce in superparamagnetic. So why this is a very important requirement to produce magnetic fluid. Interestingly, in the second data, in the middle data, the middle picture, we can see in here the magnetization drop from about 40 mho per gram to less than 1 mho per gram. Why be like this? We know that chromium with smaller magnetic moment compared than iron 2 plus or iron 3 plus. Although we know that chromium initially is paramagnetic, but when the chromium ion inserted into Fe3O4, it become combination from super paramagnetic and paramagnetic. And in this figure, in the middle figure, we can see in here the purely paramagnetic. But more interesting in here, for the last figure in here, by inserting the...
Excuse me, Dr. Taufik.
Yeah.
Your time is 2 minutes left.
Okay, we have 2 slides. 1 slide, 1 minute. It's okay. Okay. The magnetization increased significantly. So we can see in here this characteristic become good advantage to be applied in harvesting agent. We can see in here for current versus time, there are at least 2 phenomenon. The first one is oscillation. In the physics, this is harmonic oscillation. However, because the losing energy between friction in the air or in the system, the longer the time, the amplitude of current, the lower. But the longer the time, we can see in here, the wavelength in here become more stable. This is the first advantages. The second one for the voltage in here, this is the last slide. This is more stable than the current. So we can convert in here from this voltage measurement, we can see by inserting some doping with other metal, we can produce magnetic fluid with a better performance for energy harvesting agent. And for the conclusion, I think we have successfully fabricated stable ferrofluid from natural sand with high impurity, with high excellent magnetic properties to be applied as energy harvesting agent. Thank you very much.
Okay, Dr. Taufik, thank you for your inspiring presentation. We invite the participant to ask one question to the presenter. Can I ask one question, Dr. Taufik? Can I ask one question?
Yes, please, Dr. Irma.
Okay. In drug delivery use, your application of your material is drug delivery use. I want to know how you test the compatibility of the coated nanomagnetite in vitro and in vivo scale. What are the test steps? What are the test steps?
Okay, very good question. We have already investigated both in vitro or in vivo and in vivo investigation. Last year, exactly 2 years ago, before pandemic, we have already ordered a human cell from Singapore. So we have already used this one for antibacterial, antifungal, and also another test. And also we have produced some papers based on 3 years ago for anti-cancer. So we already finished this measurement for biomedical and also medical application. But for this year, after pandemic, we focus on how to produce magnetic fluid or ferrofluid with harvesting agent, because this is new phenomenon in physics. If we see in here, it is very difficult to find a paper related ferrofluid to produce harvesting agent. So in vitro or in vivo have already finished in our work. We already made collaboration with several universities, including with Thailand, with Malaysia, and also with University of Tokyo. So this is very easy to investigate the ferrofluid for in vivo or in vitro. Maybe for the next time, Dr. Irma can make collaboration with us. I know that your work is also good, especially in you have very expert. You are very expert in chemical synthesis. So I hope this work, this project will give more impact, not only for publication. I think publication is easy, yeah, but also for application in order to be applied in real world, in real industry. I think this is our target for the next time. Thank you.
Okay, thank you for your offer, Dr. Taufik. Okay, thank you very much for your interesting sharing. Today, we will follow the next presentation. The next presenter is Henry Siswanto. The effect of the title of the presentation is the effect of energy compaction on Marshall performance of asphalt concrete. Thank you very much, Dr. Taufik. The next presentation.
I am Henry Siswanto. Allow me to present my paper with title of Effect of Energy Compaction on Marshall Performance of Asphalt Concrete Wearing Course. I am accompanied by Pranoto, Bambang Supriyanto, and Viko Renanda Pratama. The background of my research is Indonesian road condition. We can see here that in Indonesian road condition, there are 3 levels of administration road. Here, the first one is national road in good condition around 93%, followed by provincial road 68%, and the last one is Regency road 54%. So in average, is Indonesian condition road is not good. So that's need a solution. One of condition maybe a probability about less compaction or inadequate compaction. There is a common problem of asphalt pavement. Some literature said that compaction is an important factor. So there is some question. Performance of road condition is it caused by less compaction on inadequate compaction, or there is no optimal compaction in a site. That's the question. So that question, we have to need some research, and the research here I have to create some, the objective. The objective of research here is to analyze the influence of compaction energy on asphalt concrete during course performance. The approach is a laboratory scale, namely by using of Marshall parameter analysis. Marshall parameter analysis consists of 6 parameter here. The first is stability, flow, VMA, void, fill, asphalt, and MU, Marshall equation. And the flow chart here, we can see from the first one is Marshall specimen. We have to prepare Marshall specimen. After that, the Marshall specimen should be tested by Marshall apparatus, and after that we have to analysis to get optimum asphalt content. And in the condition of optimal asphalt content, and then we create Marshall specimen also with variation of blows, and number of blows is 20 until 95 blows in ring of 5 blows. And then the result of testing should be analysis, and then the last is discuss and conclusion. This is the result of my research. We can see that stability and number of blow here from 20 blows until 95 blows, the stability in the trend of increase. Even the maximum increase here, we can see that in 75 blows. And flow from 20 blows until 95, we can see the trend is decrease. Even in there is a maximum decrease here in the blows of 75. And then this is the data of PMA. PMA is void in mineral aggregate. The relationship between VME and number of blows, here we can see also that decrease from 20 blows until 95. Even here there is a maximal increase in point of 70. So different with before, this is 70, not 75. This is the data of unit weights. And the data of unit weights from 20 blows until 95 blows. We can see also in the maximum trend, there are 3 points here, 70 and 75 blows. And MU is Marshall equation. Marshall equation is a comparison between stability and flow. The data, we can see also that the trend of increase, even increase until 75. After 75 is data is not consistent here. There is a decrease, then under that increase. This is film void in MIG. The data like this from to 20 plus decrease in to specific value, that is 75 plus. After that there is increasing of the data, and this is VFA void filled by asphalt. We can see here the maximum result is in belows of 75. After that, there is a decreasing of VFA. After I get some data from stability, flow, VFA, and then unit weight and MQ, I get some conclusion. There are 4 conclusions. And the first conclusion, stability, MQ, unit weight, and VFA of ACBC. ACBC is asphalt concrete twin course. Increase along the amount of compaction energy and reach the maximum ACBC mixture value with 75 flows. The flows above 75 times tend to reduce stability, MQ, unit weight, and VFA. When the value of flow, VMA, and VIM of the ACBC mixture decrease with additional flows, the minimum value occur in ACBC mixture with 75 flows. The number of flows above 75 times will tend to increase the flow, VME, and VIM value of the ACBC mixture. And the last conclusion, based on the Marshall parameter, the best number of flows in ACBC mixture is 75 flows. Okay, that's all my presentation. Thank you for your attention. And finally, Assalamualaikum warahmatullahi wabarakatuh.
Okay. We will invite one question for Mr. Henry Siswanto. Mr. Henry Siswanto, are you in Gamaru?
Okay. I present here.
Okay. We invite one question.
I have to present here because I have problem in my audio laptop. So please, maybe the other one, not this, the other one. I
Okay.
present in phone here, by laptop and by phone, yeah, because I hope you can hear my voice. I'm sorry, this. Can you hear my voice here?
Okay. Okay. If there are no questions, we will proceed. Okay. Okay. We have one question. Please, the speaker mentioned the name and institution.
Thanks for saying for us. My name is Budistiana from Semarang. Yeah. Dear presenter, I would like to ask for your explanation about your conclusion number 2. Your conclusion number 2 say that the flows above 75 reduce the stability. However, the previous slide shown that the stability increase in the graphic above the 75 flows. Can you explain me? Thank you.
Okay, thank you. Can you hear my voice?
Yeah,
Yes.
yeah.
Okay, thank you.
Thanks.
Yes. My research, the data is not increase, not increase at all, but from 20 blows until 75 blows increase.
Yeah.
Yes, after that get a maximum increase, and after 25 blows, the result of stability is decreased. I'm sorry if that's my my point. Yes, that's my point.
Oh, decrease.
Yes.
Because I see that
After
your previous
25
slide,
blows,
it
yes,
is still increase.
yes.
I forget the number slide. Yeah. said
not
before.
increase at all, but after get maximum point and the 75 flows, then there is a decrease of the result.
Chris here.
Okay,
Oh, okay.
Mr. Budi, that's my explanation. I hope that this can help at you to clear my research.
Yeah, yeah.
Yes. Okay.
Okay, thanks.
Okay, welcome.
Okay, thank you, Mr. Henry. Thanks for your answer. We will proceed the next presentation. The next presentation is the next presenter is Mr. Budi Setiana. The title of the presentation is The Effect of Sliding Velocity on Friction of Rubber in Contact with a Rigid Spherical Counter Surface, a Numerical Investigation. Mr. Budi Setiana, are you available for today? Mr. Budi Setiana? Okay.
Oh, yeah. Okay.
Okay.
Yeah.
Operator, please proceed the next presentation video.
Yeah.
With rigid spherical Indian counter surface, a numerical investigation. We introduce myself that I am Budi Setiana with my friend. There are collaboration between University of I-CoRE Semarang and University of Twente, Netherlands, especially research about the contact mechanism, friction, and lubrication. My outline presentation like this: number one, background; number two, material and methods; number three, result discussion; and the last outline is conclusion. My background like this: that rubber is unique behavior than other materials. That rubber is easy to be deformed; it get some force. And application, many components of rubber are in friction contact, like tire, seals, and transmission belts. So friction contact is closely related to abrasion wear that provide a limited time in application and also braking capacity, especially on vehicle tire. Friction contact phenomena on the rubber surface is rarely studied and difficult to be performed analytically. So, my research purpose is investigate the friction contact phenomena in numerical method using numerical method. Its material and method. Number one, introduction. At first, sliding contact between rubber surface and counter surface has been modeled here. The analyzed rubber is styrene butadiene rubber that is compounded by carbon black and by silica. The counter surface is a rigid spherical indenture. It cannot be deformed along sliding. The sliding contact is carried out in various sliding velocity. In this case, my research in sliding contact analysis is using finite element method. We use abacus software that is produced by Simulaya Corporation. And finally, the rubber is modeled in a hyperelastic material. So in this software, there are some options about the material type. So we choose a hyperelastic material. Yes, and so the figure about the schematic model of sliding contact. And finite element mesh model. On the left side, show that is represent the SPR specimen, yeah, the rubber. Its boundary condition at the bottom, it cannot move in horizontal as well as vertical direction. So on the left side and on the right side, it can move in vertical direction. Yeah. In the right side, it's shown the meshing of finite element model. So we see that around the contact area, the mesh model is fine, so fine. We make it in order to find accurate result, like as deformation, stress, and contact force. Is the input and output of the nice simulation, finite element simulation. Yeah. And we choose the sliding velocity like this. We make 5, 10, and 15 millimeter per second. Yeah. So the depth of sliding or depth of penetration constant, namely 0.7 millimeter. Contact surface roughness is 0.5. It's same as the coefficient of kinetic friction. So the output of the simulation is stress and deformation of the rubber surface, and contact force along sliding, and coefficient of friction. Based on the stress pattern and deformation, stress pattern in start condition is still in static condition. So the stress pattern is symmetric because it is still in static condition. Yeah. It's a sliding condition, and the last is stop condition after sliding. So we see that the maximum stress is around below the indented on front side or leading edge of the indented surface. The upside is represent the rubber compounded by carbon black, and the bottom side is rubber compounded by silica. There's the maximum stress in vertical axis, maximum stress and MPa. Yeah. So in the horizontal axis, represent the sliding displacement. We make a 8 millimeter sliding distance. From this result, it's shown that at high sliding speed, especially on 25 millimeter per second, the value of the maximum stress is highly fluctuate. Yeah, for high sliding speed, for compounded by carbon black as well as compounded by silica. It also the same for tangential contact force. In high sliding speed, provide a high fluctuating tangential force, and also for rubber compounded by silica. It's shown the normal contact force. Yeah, normal contact force in high sliding speed, so also provide a high fluctuating condition like this, and also for SSPR, yeah, SSPR, so high fluctuating normal contact force. And coefficient of friction, it consists of 2 sections, due to deformation and due to surface roughness. It also shows that total coefficient of friction in high sliding speed also provide high fluctuating value for SPR 25 and SPR. So the experimental validation is very small case. Unfortunately, that sliding contact phenomena on the rubber is still really discussed experimentally. But we propose in two cases. Number one, contact between rigid pole glass and rubber surface that proposed by Maekawa. The results show that high sliding speed provide high fluctuating contact force. Qualitatively agree with my research. And number two is contact between a rubber sample and flat glass that proposed by Tonen. The result also found that high sliding of speed provide high fluctuating coefficient of friction. So it also qualitatively agree with my research. The final conclusion that high sliding speed provide a high fluctuating value of stress, contact force, and coefficient of friction. And long sliding, the maximum stress of the rubber occurs at the leading edge of the spherical antenna. Long sliding contact, the material SPR25 has a slightly higher responses than SSPR, especially at high sliding speed. Finally, high sliding speeds provides dynamic phenomena of the sliding contact on rubber. Okay, enough. Thanks you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Budi Setiana. We invite one question for Mr. Budi Setiana. Okay, if there are no questions, we will proceed the next presentation. The next presentation is presentation from Mrs. Grace Yohanika. The title of the presentation is Synthesis of Porous G-graphite carbonitride and its application as a photocatalyst for methylene blue degradation. Ms. Grace Yohanika, are you available for today?
Yes, I am here.
Okay, thank you. Operator, please play the next video.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. I would like to see you. Thank you for coming in my presentation. It's great to see you all. I'd like to quickly introduce myself. My name is Grace Yohaneka. I'm student from Institut Teknologi 10 November ITS, Department of Chemistry. My supervisor is Professor Dr. Joko Hartanto, MSc. And then today I'd like to share with you my presentation topic, synthesis of porous graphite carbonitride is application as a photocatalyst for methylene blue degradation. Introduction. Dye was considered as hazard was having negative impact of the environment and human health. This was produced from various industries such as textile, cosmetic, pen, and printing industry. Worldwide, around 7.15 metric ton organic dye was discharged directly into water body, which have the potential the source carcinogenic, teratogenic, and mutagenic. Hence, treatment of organic dye in water becomes significantly important. Several dye wash treatments have been developed, for example, absorption, chemical deposition, filtration using membrane. Unfortunately, the machine treatment do not completely remove the extent, so further processing is still needed. Differently, the photodegradation treatment of interesting why completely remove the dye from the water. In the photodegradation process, the toxic dye molecule can be converted into less harmful ion or molecule, or even completely decomposition carbon dioxide and water. Therefore, the photodegradation process becomes attractive strategy for water treatment. Of the various type semiconductor material used for photocatalytic degradation, graphite carbonating is considered one of the most promising material. Graphite carbonating has narrow band gap 2.7, good chemical and thermal stability, is the mass production, and is the often rare material. However, black graphite carbonatic natural has a low surface area less than meter to gram and limited number of active sets. So, a restricted combination rate photodegradation carry hole and electron become very high. Therefore, efforts obtain graphite carbonatic with a large surface area improves charge separation efficiently a great important. So this strategy is modification of the surface morphology blue graphite carbonatic to porous graphite carbonatic. Some research have reported that modification the surface morphology one set on 2019 graphite carbonatic mesophore successfully synthesis using melamine and carbonate beverage. Hydrogen evolution has showed the mesophore graphite carbonatic exhibited hydrogen generation up to 15.1 times higher than book graphite carbonatic due to its higher surface area, which provide a much higher amount active site. Jia et al. 2020. Furthermore, porous graphite carbonatic nanotubes successfully synthesis from melamine with salicylic acid as pore forming again. The porous nanotube structure showed a higher catalytic activity with one about 6.7 and 2.4 times greater than for graphite carbonatic form the 2-propanol decomposition reaction and carbon dioxide reduction. Because the higher surface area, more effective charge transfer morphology optimal. Kong et al. Porous graphite carbonatic nanosheet. Recently, citric acid was also reported as efficiently performing again for preparing porous graphite carbonatic. So the amount of the citric acid influence the surface area and the activated aerosol graphite carbonate. Problem statement: melamine at citric acid various amount of citric acid, porous graphite carbonatic, how structure property, how optimal property, how electron conductivity, and how photocatalytic activity. Experimental. The synthesis of porous graphite carbonatic. Melamine in citric acid, the mixture was heated continually for 2 hours at 80 degrees Celsius to produce a white suspension. The white suspension was then put in the autoclave heat in oven 180 degrees Celsius for 12 hours. After heating, the suspension was filtered and deionization water several times. The filtered precipitate was dry at 80 degrees Celsius for 2 hours. The dry sample were placed close porcelain crucible and calcined in a muffle furnace at temperature 550 degrees Celsius for 2 hours. And the obtained product were aside as graphite carbonatic 0, 1, 2, and 3 respective. Characterization. Characterization porous graphite carbonatic is assertive, FTS, SAM, and absorption, diffuse reflectance spectroscopy, DRS, photoillumination, Matskovsky analysis, and electrochemical independent spectroscopy. Photocatalytic activity using methylene blue degradation under UV light irradiation. The solution was allowed to stand for 1 hour under acid in the dark to raise methylene blue absorption. After 1 hour in the dark, UV lamp was turned on and 2 ml a liquid solution was taken periodically every 60 minutes up to 180 minutes. The concentration was when using UV spectrophoton in wavelength 60, 50, 59 nanometer. Result and discussion. SRT. SRT, the pattern was employed to investigate the phase structure of the sample. Peak at 2 theta around 12 degrees showed this triazine. Strong peak and around 27.5 degrees showed the interplanar stacking peak of the conjugating aromatic ring. So the gravity carbonatic has been successfully formed with high purity. The scalar equation, the porous gravity carbonatic posts lower crystalline size than that of bulk gravity carbonatic, and then PED nitroconsumption method showed the surface area in this this slide. Same. All gravity carbonatic samples have citric structure. The effect citric acid addition during gravity carbonatic show a more hole and pore in the porous gravity carbonatic compared to bulk gravity carbonatic. FGER spectra confirm the formation of gravity carbonatic structure. Addition of citric acid do not affect the structure. UV-DRS spectra of gravity carbonatic based photocatalyst showed the tiling at the porous gravity carbonatic like set to the lower energy and as presented in tau plot. The calculated band gap for gravity carbonatic 2.7 eV and porous gravity carbonatic 2.68 eV. So addition of citric acid do not significantly affect of the band gap. The photoillumination peak of all porous gravity carbonatic clearly show lower intensity compared to bulk gravity carbonatic. Porous gravity carbonatic to the lowest photoillumination peak intensity indicate the highest suppression of charge carrier recombination. So the porous structure in the gravity carbonatic can suppress the charge carrier recombination. Motzkowski plot to determine the nature of semiconductor and the carrier density. Higher slope showed lower carrier density, so gravity carbonatic 2 show the lowest slope, highest carrier density. Nyquist plot a smaller R-D indicate the smaller electron transfer resistance. Porous gravity carbonatic has smaller R-D than that of bulk gravity 0, thus getting the smaller electron transfer resistance. So porous structure on gravitic led the better charge transfer. Photocatalytic activity methylene blue photodegradation under UV light of gravity carbonatic based photocatalyst. All samples are able to degrade the methylene blue molecule under UV light irradiation. The methylene blue degradation over porous gravity carbonatic show higher rate compared to the bulk gravity carbonatic. And then the porous gravity carbonatic has higher reaction rate constant than that of bulk gravity carbonatic 0. In porous structure, charge carrier can reach the surface more efficient to react with the reactant. Conclusion. The porous gravity carbonatic was successfully prepared using citric acid as bond-forming agent. 2. The pore formation can be indicated by the smaller crystalline size of porous graphite and the higher surface area. 3. The porous formation does not have significant effect on the light absorption capacity and the band gap, but it can suppress the charge recombination. 4. The porous structure can extend the charge transfer efficiently. 5. The porous gravity carbonate show a higher methylene blue degradation rate compared to the bulk gravity carbonate attribute to the higher surface area and the better charge transfer. Thank you for attention. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you for Mrs. Grace Yohaneka. We invite one question for Mrs. Grace Yohaneka. Okay, there are no questions. Okay, we follow the next presenter. This is Aisyah Nur Hasana. Are you available for today?
Yeah, I'm here.
Okay. The next presenter is Aisyah Nur Hasana. The title of her presentation is Investigation of Manganese Ferrite Multi-Walled Carbon Nanotubes at ZNO Potential as Radar Absorbing Material. Operator, please play the next presentation video.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Thank you for coming to this presentation. It's an honor to meet you all. First of all, let me introduce myself. My name is Aisyah Nur Hasana, and I am from Universitas Negeri Malang. The title of this research is Investigation of Nanostructure and Morphology of Mangan Ferrites Multi-Walled Carbon Nanotubes Zinc Oxide Nanocomposite. I have divided my talk into a few sections. First is introduction, second is experimental method, following by results and discussion, and the last is conclusion. For the introduction, as we know that among various iron oxides, magnetate has been greatly studied due to its properties and characteristics such as high thermal stability, high chemical properties, biocompatibility, low toxicity, and high magnetic saturation. Unfortunately, magnetate has some limitation in several aspects like high density, low dielectric properties, and easy to agglomerate. On the other side, the previous work reported that doping with mangan can reduce the density of magnetides and increase its shape and surface area. However, another innovation is also necessary to enhance its the electric properties. Multi-walled carbon nanotubes has been reported that more conductive if compared to magnetides when integrated into a hybrid system. That's why multi-walled carbon nanotube can use to increase the electric value of magnetate. Although combination between mangan ferrite and multi-walled carbon nanotube is satisfying enough in several aspects, but in specific application like radar absorber materials has problems in impedance imaging that affect the reflection at close. As a result, it requires other materials to overcome the problems. In this context, zinc oxide is believed to be able to improve the appearance matching performance of nanocomposite. Besides, it also has many advantages such as high dielectric properties and high thermal and chemical stability. Therefore, in this work, it is essential to synthesize mangan ferrites, multi-walled carbon nanotubes, zinc oxide nanocomposite. The experimental method in this work was divided into 3 steps. First, we functionalized multi-walled carbon nanotubes by using nitric acid. And then we combined the functionalized multi-walled carbon nanotubes with mangan ferrite using sonochemical method, as we can see in this picture. And then the last is we combine it again with zinc oxide by using sol-gel methods, as we can see in this picture. For the results and discussion, first, I would like to discuss about the structure of nanocomposites. In figure 1, show the X-ray diffraction patterns of mangan ferrites multi-walled carbon nanotubes zinc oxide. It can be seen that there is a black one and the red one. The black represents the experimental data, and the red line represents the fitting model. It confirmed that from the X-ray diffraction characterization, we confirm the presence of the magnetite and zinc oxide phase. Besides, there is also a broad peak that represents the existence of multiviolet carbon nanotubes. From the picture, we can see that zinc oxide was the majority one. As the for detailed information, you can see that in the table. The mechanism of manganese doping ferrite was shown in the figure 2 that show the crystal structure of mangan ferrites. It can be seen that there has been manganesite that replaced ferrite atom at the tetrahedral site. Okay, the next we will talk about the functional groups of mangan ferrites multiviolet carbon nanotubes zinc oxide nanocomposite. In the figure 3, show the infrared spectra of the nanocomposites that was observed at 400 until 4,000 wave numbers. There is an absorption band of metal oxide MO, which represents absorption at wave numbers in the range of 430 until 628. From the table also, we can also see that there is a zinc carbon absorption band that represents interaction between zinc oxide and multiviolet carbon nanotubes. For more details, you can see that in the table. The next, we will talk about the morphology of the nanocomposite. In the figure A4A, you can see that there are small spherical particles representing manganese ferrite and zinc oxide materials tend to stick around the rod-shaped material, which is multiviolet carbon nanotubes. It is caused by the modification of multiviolet carbon nanotubes, which results a carboxylate surface defect and then becomes the attachment site for nanoparticles. Moreover, the addition of zinc oxide resulted in more particles covering the multiviolet carbon nanotubes. The possible mechanism to explain it is multiviolet carbon nanotubes, which has a strong absorption tendency and has been confirmed from the FTIR result, where it is shown a strong absorption between zinc and carbon functional groups. The next, we will talk about the particle size distribution of the nanocomposite is 49.37 plus minus 0.18 nanometers, that is shown in figure 4B. The next, we will talk about the ADAX spectra of mangan ferrites multiviolet carbon nanotubes zinc oxide nanocomposite that show that is composed of ferrite, mangan, carbon, oxygen, and zinc elements. According to the ADAX result of the nanocomposite, the majority of its element is zinc oxide, which one is matching with the X-ray result. That's why we can conclude that mangan ferrites multiviolet carbon nanotube zinc oxide nanocomposite has been successfully synthesized using sonochemical and social methods. The X-ray diffraction characterization analysis confirmed the presence of magnetite and zinc oxide phase and a broad peak that represents the existence of multiviolet carbon nanotubes. The result of FTIR characterizations indicate the presence of functional groups that corresponds to mangan ferrites, multiviolet carbon nanotubes, and zinc oxide. Besides, scanning electromagnetic results show that the particle size distribution is 49.375 plus minus 0.18 nanometers. And the last, EDOX crystal confirmed that the constitutive elements of mangan ferrite's multi-wallet carbon nanotubes zinc oxide are ferrite, mangan, zinc, carbon, and oxygen. This research was fully supported by the PUI Cambridge Can grant from University Negeri Malang. Thank you for your attention.
Okay, thank you for Mrs. Aisyah Nur Hasanah. Maybe we invite one question for Aisyah Nur Hasanah. There are no questions. Oh, okay, we have one question from participant. How does the dielectric properties affect performance on radar absorbing performance?
Okay, I would like to answer the question. The first is actually his research is we would like to characterization until we know about the radar absorption material, radar absorption performance of this material. But unfortunately, in the middle of this research, we can't do the characterization, so that we change this research to be the basic characterization, and we would like to develop for the next research. So until for this research, we haven't done about the characterization of the radar absorbing performance, but about the dielectric properties affect performance on radar absorbing performance is the characterization of the good materials from radar absorbing performance is with the material that have high dielectric property. So the higher the electric properties of materials, it will result more higher performance of radar absorbing materials. Is it clear?
Okay, thank you for your answer. We will follow the next presentation from Delianti. Mrs. Delianti, are you available today?
Yes, I'm here.
Okay. The title of Mrs. Delianti presentation is synthesis of manganese ferrofluid with polyvinyl alcohol, tetraammonium hydroxide double surfactant, and its application as magnetic sensor. We will follow the next presentation.
My name is Delianti. Now I'd like to present my paper with title Synthesis of mangan ferrite with polyvinyl alcohol ferrofluid and its application as magnetic sensor. Introduction. In recent years, the development of nanomaterial technology is increasingly being carried out, one of which is ferrofluid-based magnetic sensor technology. Ferrofluid was chosen because the sensitivity is not only obtained from the magnetic spin but also from the flexibility of the liquid, which facilitates the orientation of the particle to the influence of the external fluid. Related to the development of ferrofluid as a magnetic sensor application, one of the material used a filler is a magnetite. The material has super paramagnetic characteristic and saturation magnetization value. The improved the performance of magnetite for magnetic sensor application. Several alternatives can be carried out. One of with mangan doping. In theory, this doping will cause more significant saturation magnetization. The magnetate-based ferrofluid as a magnetic sensor application still has weaknesses such as having non-uniformity and weak stability. Based on Taufik et al., the ferrofluid with magnetic magnetite filler still have the stability of ferrofluid has not been maximized with the presence of aggregation. It is necessary to phenol alcohol surfactant was added in order to maintain that stability of the filler from external magnetic field and prevent aggregation so to produce dispersed nanoparticle from magnetic sensor application. Experimental methods. These research methods consist of two methods, namely the synthesis of mangan ferrite PVI ferrofluida and experimental setup of magnetic sensor, which can be seen in the picture. Result and discussion. The diffraction pattern of mangan ferrite PVI are representation in figure 1. The diffraction peak indicated that the nanoparticles are performing at angle to theta, which can be seen in the table. That the high peak intensities of the mangan ferrite is to theta 13.5.13, which corresponding to peak of the cubic structure of magnetite phase. With lattice parameter and crystal size, we can be seen in the table. In this study, no peak seed and no peak performed other the magnetite after addition of PVA indicated that nanoparticle probability level was high. The sample analysis from a spinel cubic crystal structure in the presence of Fe tetrahedral site, oxygen, and Fe octahedral. That the emergence of mangan site that replace tetrahedral Fe atom as figure 2. FTIR. Shown the result of spectrum analysis FTIR in figure 3, representation the vibration of functional group and vibration wave number contained in nanoparticle mangan ferrite PVA can be seen in the table. A morphology of mangan ferrite PVA sample and the particle size distribution can be seen in figure 4. Morphology mangan ferrite PVA is a spherical nanoparticle with a fairly uniform particle size distribution with little agglomeration. The particle size distribution in this study was 39 nanometer. Element analysis of mangan ferrite PVI nanoparticle has been carried out in table 1. Based on the table shown, the nanoparticle contain ferrum, mangan, and iron element in mass presentation of confirm that nanoparticle had high purity. Magnetic sensor of mangan ferrite PVI. A magnetic property test of ferrofluid mangan ferrite with surfactant PVI was carried out by observing the effect of laser light of the magnetic field applied to the ferrofluid. This study used a magnetic field in the range of 0 to 18.5 MT, where the more significant the magnetic field detected, the aggregate in intensity rate by the ferrofluid. It can be seen from the measure result the magnetic field volume ratio 80 MT with intensity volume 121 lux. The XRD result analysis confirmation the nanoparticle size for 8.14 nanometer. The functional group that present the percentage of mangan ferrite PVA participle and dispersion again carbon hydroxyl, carbon-carbon alkyl with indication the presence of PVA group. Same ADX result present the spherical shape with a particle distribution 39 nanometer. The result of the mangan ferrite PVA perovskite testing showed the magnetic field current result to the light intensity. Perovskite indicated the light intensity increase with the increased external magnetic field. Next, this is my whole presentation. Thank you for attention. Good afternoon.
Thank you for Mrs. Delianti. Maybe we invite one question for the Mrs. Delianti. Okay, Mrs. Gama, please you give your question.
Yes, thank you for the chance, Mistress Moderator. So I want to make sure with the presenter, can you explain how the effect of adding polyphenol alcohol in magnetite, manganese magnetite, about crystal structure of manganese magnetite with polyphenol alcohol? Thank you.
Okay, thank you. My question.
Hello everyone. I'm sorry we are having technical difficulties at the moment. Please stay in this room.
Okay, thank you. My question. After addition PVA result XRD show, the size lattice parameter is small and no peak shift and no peak performance of the magnetic in indication the nanoparticle purity less was high.
Ya, semuanya kok. Tadi ada yang ngetuk saya.
Okay, Mrs. Gama.
That's enough. Thank you.
Okay, thank you. Thank you for Mrs. Delianti. The next presenter is Arifa Nurlaili. Arifa Nurlaili, are you available for today? Mrs. Arifa? Mrs. Arifa? Okay, Mrs. Arifa Nurlaili, are you available for today?
Yeah.
Okay, please operator, proceed the next video.
Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen, and how to meet you in this beautiful day. Thank you for coming to this presentation. I would like to share about lead 2, nickel 2, and cobalt 2 ion absorption by lead 2 imprinted crosslink carboxymethyl kappa carrageenan code nanomagnetic. Let me introduce myself. My name is Arifan Nurlaili. First, I will explain to you about introduction. The aim of the research to synthesize ion selective adsorbent lead to imprinted crosslink carboxymethyl kappa carrageenan code nanomagnetic to measure the adsorptivity of the adsorbent to adsorb lead 2, nickel 2, and cobalt 2. Experimental procedure. For the first step, synthesis of nanomagnetic by the co-precipitation method. Second step, synthesis of carboxymethyl kappa carrageenan from carrageenan with natrium hydroxide and monochloroacetic acid. Third step, synthesis of nanomagnetic code with crosslink carboxymethyl kappa carrageenan imprinted with lead 2 ion. For the fourth step, adsorptivity test of the adsorbent to adsorb lead 2, nickel 2, and cobalt 2 ion. Synthesis of characterization of nanomagnetic scanning electron microscope. The result of magnetic morphology analysis by scanning electron microscope. The average size of magnetic is 28.25 nanometer, indicating that the synthesis magnetic may have a nanometer size. Fourier transform infrared spectroscopy. The Fourier transform infrared spectroscopy typical peak of nanomagnetic appears at 569 and 640 correlate to FAO intrinsic. X-ray diffraction. The formation of a magnetic was indicated from the appearing of 29.8, 35.47, 43.28, 56.98, and 20 and 62.65 peak the relate to the standard magnetic pure X-ray diffraction patterns of observed. Carboxymethyl kappa carrageenan scientists from kappa carrageenan, the reaction equation of carboxymethyl kappa carrageenan shown below. Fourier transform infrared spectroscopy. Based on the Fourier transform infrared spectroscopy spectrum, it appears that some of the hydroxyl group have been replaced with carboxyl group, indicated by the appearance of absorption peak at wave number 1602 and 1423 confirm the formation of CU group. Scanning electron microscope lead to imprinted crosslink carboxymethyl kappa carrageenan code nanomagnetic. Nanomagnetic coat with carboxymethyl kappa-carrageenan cross-linked with citric acid and imprinted with lead-2-ion, then characterized by scanning electron microscope and Fourier transform infrared result analysis appears some folding on the surface of nanomagnetic coat with carboxymethyl kappa-carrageenan cross-linked with citric acid and imprinted with lead-2-ion. The fold occurred due to the shortening of the distance between the chain and the binding knot. Result a wavy texture and the average size of absorbent is 63. The synthesis material lead to imprinted cross-linked carboxymethyl kappa-carrageenan coat nanomagnetic. There are some peaks indicating the presence of symmetrical and asymmetrical vibration of carboxyl anion, identical with the off-symmetrical and asymmetrical vibration of carboxymethyl kappa-carrageenan. Carboxyl anion, which appears in the wave number region 1600 until 1650 and 1450, that indicates asymmetric vibration of the carboxylate anion. The absorptivity of metal ion by lead to imprinted cross-linked carboxymethyl kappa-carrageenan coat nanomagnetic shown below. It can be seen that the synthesized absorbent was able to absorb lead-2-ion higher than other metal ion in sample containing one type of metal ion, as well as sample containing a mixture of metal ion. Conclusion: absorbent lead to imprinted cross-linked carboxymethyl kappa-carrageenan coat nanomagnetic has been synthesized. The absorbent able to absorb lead-2, nickel-2, and cobalt-2 ion from sample containing single ion and the mixture of lead-2, nickel-2, and lead-2, cobalt-2. The absorbent tend to absorb more lead-2 ion than nickel-2 and cobalt-2 ion. Thank you.
Okay, thank you for Mrs. Arifa Nurlaili. Maybe we invite one question for Arifa. Okay, there are no questions. We follow the next presentation. Baik Rosari Fortuna. Baik Rosari, are you available for today?
Yes, I'm available.
Okay. The presentation of Baik Rosari Fortuna, the title is Preparation of Magnetite, diethylamine, PMH, ferrofluid, and their performance as energy harvester. The operator, please play the next video.
Good afternoon, everyone. I would like to present my paper with the title Preparation of Magnetite Diethylamine Tetramethyl Ammonium Hydroxide and their Performance as Energy Harvester. Since the last 5 years, the development of power plants in Indonesia has focused on developing renewable energy-based power plants. The main focus of designing a renewable energy mechanism is the creation of energy harvesting system. Electromagnetic induction is the concept of energy harvesting by generating an electric current due to change in the magnetic field. Electromagnetic induction-based energy harvesters have been developed in the form of magnetic liquids, such as ferrofluids. One of the potential materials to be used as the ferrofluids material magnetite nanoparticles. The performance of magnetite ferrofluid as energy harvester still has limitations, such as its tendency to agglomerate, which might affect the attraction of ferrofluid with an external magnetic field. One of materials that can be used to reduce the level of aggregation in magnetite nanoparticles is the addition of diethylamine polymer surfactant. It is necessary to add tetramethyl ammonium hydroxide as a stabilizing agent by keeping the magnetite nanoparticle in solution from agglomeration as to improve the performance of ferrofluids as energy harvester. So, magnetite nanoparticles with surfactant, diethylamine, and tetramethyl ammonium hydroxide as ferrofluid stabilizing agents are able to enhance the performance of nanotite ferrofluid as energy harvester. So this is the scheme of synthesis of magnetite, diethylamine ferrofluids, and nanoparticles. The next one is the figure shown in the screen is the scheme of testing magnetite, diethylamine, tetramethyl ammonium hydroxide ferrofluid as energy harvester. So this is the results and discussion for crystal structures of magnetite diethylamine nanoparticles. In figure 1, it can be seen that the diffraction peak from indicated the presence of magnetite diethylamine nanoparticles by occupying the corresponding Miller indices that's shown on the table. Based on the results of refining, the latest parameter values and crystal volume were identified from the experiment data, namely I-CoRE 36 Armstrong and 5084.28 Armstrong cubic, respectively. Furthermore, through the refining step, a particle size of 30.3 nanometers was obtained. The results indicate the use of diethylamine as a surfactant has success in reducing the particle size of magnetite. In figure 3 shows the infrared spectra of magnetite diethylamine nanoparticles, representing the vibration of functional groups and vibrational wave numbers contained in nanoparticles. Magnetite diethylamine can be seen in the table. In figure 4 shows the scanning electron microscopy image of magnetite diethylamine nanoparticles. Based on the measurements carried out, the particle size distribution values were obtained in the interval from 10 to 90 nanometers with an average particle size of 47.3 nanometers. Identification of elements in magnetite diethylamine nanoparticles was also carried out along with morphology. The results obtained show representative results for magnetite compounds which have two major constituent elements, namely Fa and O. The weight percentage of the two elements are 69.5% and 30.5% respectively. This test was conducted to determine the two main electrical parameters, namely induced current and induced voltage with respect to time. The graph that connect the two sequentially are shown in figure 5 and 6. It is calculated that average output induced current is 0.87 microampere, while the average output induced voltage is 4.87 microvolt. The results of the voltage and current induction were influenced by the success of ferrofluid synthesis with magnetic diethylamine nanoparticle as the filler. Magnetite diethylamine nanoparticles with minimal levels of aggregation were shown and a particle size of 13.3 nanometers, so they tend to have an optimal type response when an external magnetic field is given to generate electrical energy. In addition, ferrofluid based on magnetic diethylamine nanoparticles with tetramethyl ammonium hydroxide as a surface stabilizer could cause magnetite not to be easily oxidized. Colloidal suspensions also tend to be stable so that superparamagnetic characteristics are maintained and can interact with coils to produce optimal change in magnetic field flux. So the conclusion is ferrofluid magnetite diethylamine tetramethyl ammonium hydroxide has been successfully fabricated from iron sand. Magnetite diethylamine nanoparticle as a filler show a single magnetite base in with a lattice parameter of 8.36 Armstrong with a crystal volume of 5,084.28 Armstrong cubic. The identified particle size in a 13.3 nanometers. The success of the formation of magnetite diethylamine nanoparticles is also supported by the results of characterization of functional groups. Morphological analysis show agglomeration phenomenon with an average particle cluster size of 47.3 nanometers. The results of the electrical test that became the basis of determining the performance of energy efficiency show low but prospectively results. That's all. Thank you for attention and Assalamualaikum warahmatullahi wabarakatuh.
Thank you for Ms. Gamma. Thank you for the presenter. Maybe we invite one question for Baik Rosari. Okay, there are no questions. We follow the next presenter, Istiqomah. Istiqomah, are you available?
Yes, I'm here, Miss.
Okay. The title of Istiqomah presentation is The Effects of Mangan Oxide Nanoparticle Activated Carbon Composite on its Electrochemical Performance or Symmetric Supercapacitor.
Hello, ladies and gentlemen. I'm Istiqomah, master student of Universitas Negeri Malang. Today, I'd like to present our works. It's about the effect of MnO2 nanoparticles activated carbon composites on its electrochemical performances of symmetric supercapacitor. Electrical energy storage devices form an integral part in power system and electric hybrid vehicles in the form of storage components. In the field of energy storage, two main parameters are fundamental for storage devices, the energy density and the power density. The first parameter defines the amount of energy that can be stored in a given volume or weight, while the second parameter describes the speed at which energy is stored or discharged from the device. The ideal storage device should simultaneously have both high energy density and high power density. Hence, the integration of conventional primary energy storage units, such as batteries and the electric energy storage devices in the high power or pulse power forms supercapacitors becomes the prime concern in the development of new power system. Because we are working on the batteries, but the batteries sometimes during chemical reaction, it can generate some kind of toxic gases. It can corrode and it also does not have that longer life. So that's also having limitation. One kind of energy storage which getting an awful lot of interest is supercapacitor. It's renewable energy. It will not generate any kind of toxic gases. It's not harmful to the humankind. The efficiency of energy storage devices depends on structure and properties of the component materials. The supercapacitor active electrode material is activated carbon, which has a large specific area and excessive pore size distribution. However, the carbon material has a limited energy density of approximately 200 farad per gram, thus limiting its application as energy storage source. Therefore, transition metal oxides with pseudocapacitive properties and high conductivity are needed. Manganese dioxide, or MnO2, is a metal oxide which have high capacitance due to the reversible redox reaction on the surface of the active electrode. MnO2 is promising as a supercapacitor electrode material because of its significant advantages. Besides other material oxides such as high specific capacitance, safe, environmentally friendly, affordable price, and abundant availability in nature. MnO2 has a mesoporous cavity which impacts the process of charge storage and provides faster ion transport. The mixing process of AC MnO2 composite solution used the blending method. First, dissolve 1 gram of SBr in 2 ml of ionized water, then added carbon black powder, activated carbon, MnO2, and stirred for 24 hours. The composite solution was deposited on the aluminum foil substrate using the Dr. plate method and annealed in an oven of 50 degrees Celsius for 24 hours. The assembly process was done to combine the working electrode, separator, and electrolyte. Then the electrode was analyzed using X-ray diffraction and charge-discharge instrument. Here the exertive pattern, the diffraction pattern of MnO2 and composites of MnO2 activated carbon are illustrated in figure below. The X-ray diffraction pattern corresponds to the Ramsdale MnO2, where the peaks identified at 2 theta 37, 38, 43, and 57. The diffraction peaks of air MnO2 were indexed according to COD 810349, indicating an orthogonal unicell with base group of P and AM. The crystalline size of MnO2 is 5.29 nanometers. The AZCB composites show weak peaks at 2 theta of 23 and 44. The intensities was found to increase as the concentration of MnO2 increased. AC MnO2 composites with various mass showed different diffraction peaks intensity at 2 theta of 38. The charge-discharge technique is widely used in capacitor characterization. In this study, we will only focus on the charging and discharging at a constant current. The charging process in figure below, the supercapacitor is charged at a constant current with the voltage change from the discharge state to the maximum operating voltage. This figure shows the charge-discharge curves using a 2-electrode test cell in which 2 electrodes are identical or symmetric cell. The curves were triangular profiles due to the redox process resulting from the AC MnO2 composites, which indicates good electrochemical reversibility with specific capacitance derived from the combination of EDLC and pseudocapacitance. This imperfect curve was caused by a voltage drop or EF drop. EF drop is a sudden voltage drop, which commonly occurred when a supercapacitor changed from a charge to a discharge state, caused by the combination of electrode ohm resistance, electrolyte, ion transfer in the electrode material, and contact voltage in the electrochemical system. The smallest EF drop was owned by the 15% AC MnO2 symmetric supercapacitor, which only reached 0.07, which indicates that the charge-discharge cycle was stable and was not decreased drastically. This charge-discharge measurement uses a current collector, such as aluminum foil, with a voltage range of 2.5 until 2.8. The capacitance depends on the current density, potential window, and discharge time. The capacitance can be classified according to the charge storage capability of the active electrode materials or devices. In the study, we used gravimetric capacitance in farads per gram. AC MnO2 15% exhibit competitive specific capacitance value of 52.87 farad per gram. indicates good electrochemical performance caused by the ion transfer. From the figure and table below, the most optimum supercapacitor performance was the electrode with 15% MnO2 due to the decreased internal resistance and transfer electrolyte ions. However, the decreased capacitance in 20% AC MnO2 was due to resistance that inhibited reaction between MnO2 and the electrolyte. The stability of electrochemical performance through the discharge characterization were obtained at a current density of 0.1 ampere per gram, are presented in figure 1. The specific capacitance of 15% AC MnO2 decreased rapidly, demonstrating high retention capability. The highest capacitance retention when 15% AC MnO2 supercapacitor electrode, which decreased capacitance by 9.41 farad per gram, as shown in figure 1. This good capacitance retention had an impact on the life cycle of the supercapacitor, which the 15% AC MnO2 electrode could last up to 82.23% after 100 test cycles. That showed in figure 2, good cycle stability indicates that the AC MnO2 composite absorbs ion efficiently, promoting faradic reaction is highly reversible. Furthermore, energy density refers to the energy storage capability of an electrode material or a supercapacitor in watt-hours per kilograms. Power density is the rate capability of energy delivery of a supercapacitor in watts per kilogram. The 15% AC MnO2 supercapacitor electrode were achieved 21.84 watt-hours per kilogram and 344.94 watt per kilogram, respectively, due to their larger capacitance and time. The optimized electrode provided excellent electrochemical stability as promising for high energy density supercapacitor. For the summary, SC MnO2 composite had been successfully prepared with 5.29 nanometers crystalline size. The symmetric supercapacitor AC MnO2 gives rise to a specific capacitance of 52.87 farad per gram. At operating potential window of 2 volt, the maximum energy density of 21.84 watt-hours per kilogram and power density was 344.94 watt per kilogram. The 15% AC MnO2 composites offered long-term cycling stability with 82.23% capacity retention after 100 cycles. Last but not least, I'd like to say thank you to the Ministry of Research and Higher Education for funding this work. This research was supported by Kempi of Universitas Negeri Malang. Thank you and glad to see you.
Okay, thank you for Istiqomah. We invite one question for Istiqomah. Okay, there are no questions. If there are no questions, we follow the next presenter. The next presenter is Nadia Ayu Astarini. Nadia Ayu, are you available today?
Yes, I am, Miss.
Okay. The title of Nadia Ayu Astarini presenter is Performance of Nitric Acid and Ethyl Cellulose for Improvement Dye-Sensitized Solar Cell.
Good afternoon, ladies and gentlemen. First of all, let me to introduce myself. My name is Nadia Ayu Astarini. I am a master student from the Department of Physics, Universitas Negeri Malang. This is a wonderful chance for me to present our research in International Conference on Renewable Energy with the title Performance of Nitric Acid and Ethyl Cellulose for Improvement Dye-Synthesized Solar Cell. The authors in our research are Nadia Ayu Astarini, Ahmad Al-Fatihhat, Marcus Diantoro, Nasibuddin, Herlin Pujiarti from Universitas Negeri Malang, and we collaborate with Rahmat Hidayat from Institut Teknologi Bandung. This is the outline for our presentation: introduction, experimental methods, results and discussion, conclusions, and acknowledgement. The development of efficient energy conversion has attracted significant attention due to the more limited availability of conventional energy. There is need to be a greater progress on renewable energy to replace the decreasing fossil resources. Solar energy is the most available source on Earth to fill energy needs of 18 terawatt per year. In our research, we choose dye-synthesized solar cells because DSSC have a good characteristic: low cost, low toxicity, simple production process, environmentally friendly, and relatively high conversion efficiency. And our research, we choose the IO2 as a photoanode on the SSC system because they have good characteristics. They are inexpensive, non-toxic, has a high surface area, high dye absorption ability, and good chemical stability with a wide bandgap of semiconductor 3.2 electron volt. The important components in the formation of TiO2 paste, they are solid content, solvents, and organic compounds as the binders. In the previous research, water or simple alcohol are not suitable for screen printing methods because cracking will occur after annealing process by rapid evaporation. So the addition of acids effectively solves the problem of cracking on the surface of photoanodes. The acid treatment have a good advantage for photoanode, prevent charge recombination, give a effect protonation to counter anion desired scattering, and TiO2 based on nitric acid lead to increased current density with the result 15.4 milliampere per centimeter square and efficiency result 6.6%. So, in this work, we studied about TiO2 based on nitric acid and ectocellulose to show the performance photovoltaic to improvement efficiency in the SSC application. There are experimental methods in our research. Start from cleaning FTO. For first layer, we made blocking layer, and second layer, we made mesoporous layer with the two variation of TiO2 based nitric acid and TiO2 based ectocellulose. And then we treat with post-treatment and sensitizing photoanode with the N719 dye. This is the design and fabrication of the SSC in our research. Figure 1 shows the sandwich structure of dye-synthesized solar cell, and Figure 2 give information about illustration of the SSC fabrication process. Our sample were characterized in 4 characterizations. They are XRD, SAM, Solar Simulator, and ACE. This is the result from XRD characterization. Figure 3, we can see that the X-ray diffraction pattern of TiO2 films and crystal structure TiO2 anode surface. From table 1, we can see that TiO2 based nitric acid with the post-treatment have a small crystalline size Therefore, only a few photons are successfully converted into electrons. This is the refinement plotting of the TiO2 photoanodes using Reatica software. From this table, we can see parameters from fitting analysis. Our sample have a fit with the crystallography open database with the number 2310710 with the chi-square 1.3. This is the result from SAM characterization. Our sample reveals that have spherical shape and high porous particle. From table 2, we can see that TiO2 paste and nitric acid with post-treatment have a high particle distribution. Surface area TiO2 paste nitric acid assembled together and more compact well formation. This is the result from solar simulator characterization. From this characterization, we can see the GV characteristic of the DSSC system. And table 3, we can see that TiO2 paste nitric acid with post-treatment give a high current density and high efficiency. The best photovoltaic performance because NO3 ion in nitric acid blocks the path of backward electron transfers. This is the reason that the TiO2-based nitric acid optimizing dye absorption process, increasing the light harvesting ability and increase photovoltaic performance. This is the result from ACE characterization. From figure 7, we can see Nyquist plots of TiO2 photoanodes. From the table 4, we can see that TiO2-based nitric acid with the post-treatment have a low charge transfer resistance, low RCT, increase and resulting higher efficiency. RCT equals to 10 ohms and efficiency equals to 3.59%. The conclusion in this research are TiO2-based nitric acid with post-treatment process suppress the crystal size, increase the particle distribution, increase the efficiency, and decrease charge transfer resistance. This increase in conversion efficiency can be attributed to the high light harvesting efficiency and good electron transfer mechanism in the SSC system. It may indicate that TiO2 film with post-treatment have a better interconnection for the SSC system. I will say thank you for Universitas Negeri Malang from Ministry of Research, Technology and Higher Education Indonesia to support our research. For the last, I will say thank you for I-CoRE to this opportunity. See you in other change. Thank you very much.
Okay, thank you for Nadia Ayu. There are questions for Nadia Ayu. Okay, if there are no questions for Nadia Ayu, we follow the next presenter, Nabila Soleha. Nabila Soleha, are you available?
Yes, I am.
Okay, the title of Nabila Soleha presentation is The Effect of Growth Duration Using Hydrothermal Synthesis on Zinc Oxide Nanorod Titanium Dioxide FTO Microstructure.
Okay, good afternoon. I am Nabila Soleha from Physics Department of Universitas Negeri Malang. Today, I would like to present our current research entitled The Effect of Growth Duration using Hydrothermal Synthesis on Zinc Oxide Nanorods TiO2 of FTO Microstructure. First of all, zinc oxide is classified into 6 semiconductor which possess a wide bandgap around 3.37 electron volts and also has free excitatory binding energy, great optical gain, and also exceptional mechanical and high-end thermal stability. Zinc oxide is specifically attractive for a wide range of functions as if conductive oxide, anti-static coatings, touchscreen sensors and panels, and high bandgap of the electronic devices. Besides that, another material, so-called titanium dioxide, is a metal oxide semiconductor that can be known as a materials with great physical and chemical properties with excellent light sensitivity with their anodized phase with bandgap around 3.2 electron volts and also has good reliability in the environment and also low synthesis cost. Previously, TiO2 was being studied intensively as a photoanode material due to low manufacturing costs and high energy conversion efficiency. However, there's a limit to the increase in the rate of electrons due to the loss of electrons that occur during the charge transport process. Thus, to meet this problem, zinc oxide will be composited with TiO2 to become a semiconductor coating materials for photoanodes because it has higher electron mobility than TiO2 so that it can help in the process of electron transport. In this research, the zinc oxide will be synthesized in form of one-dimensional nanostructures like nanorod because it can provide a direct pathway for electron transport. Besides, materials such as substrate-oriented nanorods are known to have efficient transport properties so that they can achieve good device performance. This zinc oxide nanorod was made by the hydrothermal methods. So there are some parameters that own a notable effect on the morphology, aspect ratio, and overall efficiency of the synthesized zinc oxide nanorod structure. Some main parameters in hydrothermal synthesis, in example like precursor concentration, precursor pH, growth time, growth temperature, hexamine, seeding, and also annealing. In principle, the growth of the nanorods will show the same trend on the lateral and longitudinal ways based on the observed long-term synthesis. So in this research, we will go and investigate the microstructure of the controlling nanorod by its growth duration time with variation of 1 until 5 hours and composite them with TiO2 on FTO substrate. And the next one is the experimental method. The first visual was the FTO substrate using DI water, acetone, and also ethanol in an ultrasonic bed for 15 minutes. Secondly, we synthesized the zinc nanosheet using the zinc acetate solutions, and then we deposited it on the substrate by spin coating methods. After that, before we start the hydrothermal process, we should make the growth solution using zinc nitrate with hexamethyltetramin in the ratio of 1:1. And then the hydrothermal was carried out for the variation growth durations. And also the last one is composite the film with TiO2 by using titanium tetraisopropoxide with dip coating method. And this is the XRD data results in the form of a graph of the relation between the intensity and the diffraction angle as shown in figure 1. The peaks of the diffraction show the crystalline phase of the zinc oxide. Several zinc oxide peaks with a worst phase were identified in the HKL 100, 002, 101, 102, and also 103 planes. But the TiO2 cannot be identified when matched with the database. So this indicates that the TiO2 phase is not formed, or maybe it's formed but not in a crystalline phase. Furthermore, the crystallite size is calculated using the scalar equation, and the process of the fitting of the peak, we use pseudovoid functions. And the crystallite size of the crystal obtained on each HKL of 002, 100, and 101 planes were written in the table 1. So it shows that the crystal grain size is not significantly affected by the hydrothermal durations. This is due to the position of peak of the sample, which doesn't have much effect on these two parameters. So this causes the two parameters. So this causes the crystal grain size analyzed by the scalar equation to be not constant with respect to hydrothermal duration as shown in the table 1. And the next is for the crystallinity of the zinc oxide nanorods TiO2 samples. The results are presented in the table 2, and this crystallinity of the samples increase relative to the increase in hydrothermal duration but decrease in the variation of 2 hours. And this is the surface morphology of the with TiO2. So this, and the next is for the crystallinity of the zinc oxide nanorods TiO2 samples. The results are presented in the table 2, and this crystallinity of the samples increase relative to the increase in hydrothermal duration but decrease in the variation of 2 hours. And this is the surface morphology of the zinc oxide nanorods, TiO2 films that was studied through some characterizations. So it can be seen that the zinc oxide nanoroots TiO2 composite film has succeeded in forming a nanoroot with hexagonal structures. And this is for the EDX results. The EDX results shows that the sample contain elements of zinc, oxygen, and also titanium derived from the zinc oxide nanoroots and TiO2 materials. It can be seen in the table 3, the composition of 8% from the zinc increases with the increasing hydrothermal durations in the sample for 1 hour until 4 hours, and then decreases with the variation in variation 5 hours. The decrease in weight percent in the fifth samples may be due to the hexamine composition during the hydrothermal process, which function as a kinetic buffer for the pH of the solutions. It was caused by the initial process in the hydrothermal method that zinc 2+ ions and the pH level of the precursors were almost identical, but as the growth of the time, the concentration of zinc 2+ ions will decrease and the pH of the precursors increase. And the last one is the diameters and porosity of the samples. It's carried out using images. So it's shown in the table that the diameter with the smallest size is formed by the sample with a hydrothermal duration of 2 hours, where it also has the highest porosity with 74.48%. To the conclusions, a thin layer of zinc oxide nanoroots has been successfully grown on FTO substrate by hydrothermal method. Similar results shows that the smallest diameter of the nanoroot is 82 nanometers that also possess the highest porosity of 74.48%, and the EDX results show that the elements of zinc, oxygen, and titanium have been successfully treated. Thank you.
Okay, thank you for Nabila Soleha. We invite one question for Nabila Soleha. There are no questions for Nabila Soleha. Okay, we follow the next presenter, Diana Fatmawati. Are you available today?
Yes, I am.
Okay, the title of Diana Fatmawati presentation is coating of cotton fabric with zinc oxide graphene composite to improve water repellent properties.
My name is Diana Fatmawati. I'm from Universitas Negeri Malang. I will present the result of my research entitled Coating of Cotton Fabric with Red and Graphene Composite to Improve Water Repellent Properties. The following is an outline that I will describe. The first one is introduction. This research was carried out because of pandemic that required people to use medical masks when they were outside. The use of disposable medical masks during the pandemic has increased. This leads to scarcity, increased waste, and new environmental problems that have an impact on the future. To overcome this problem, the CDC and World Health Organization recommend using cloth masks that have features similar to medical masks. In general, fabrics are soft, not hard, or breathable, comfortable, warm, easy to absorb sweat, and inexpensive. The raw material used in making cotton cloth is cotton that has a large number of hydroxyl groups on its surface, causing the cotton fabrics to be hydrophilic. So, to make a cloth mask that has the same properties as a medical mask, It is done by modifying the surface to become a superhydrophobic layer using ZNO graphene composite. This method using a hydrothermal method and spray coating. The first step is to clean the cotton fabrics. The next step is to make a solution used for seeding nanorod. And the third step is to grow ZNO nanorod using the hydrothermal methods. And the last is to coat the ZNO nanorod cotton with graphene. The next is result. This result explain about exact pattern of ZNO graphene. This pattern of ZNO has a word-Z structure. Sharp and narrow diffraction peaks indicate that the sample is well crystallized. This table shows that strong diffraction of ZNO graphene and cotton fabrics. The ZNO crystal size is calculated using the Scherer formula. Based on the calculation that have been carried out, the average size at concentration of ZNO can shows at this table. This is accordance with the Scherer formula. If the theta is getting smaller, the particle size will be smaller and vice versa. The next is same image of ZNO graphene. This figure shows the surface morphology that has been coated with ZNO graphene at different concentration. The concentration 0.1 molar for Z1, 0.2 molar for Z2, and 0.3 molar for Z3. The next is figures confirm that as the concentration increased, almost all fabric fiber was covered with ZNO nanorods and graphene nanoseeds. This was also influenced by the large particle size in accordance with the XRD result obtained. The surface porosity calculation shows that porosity of the cotton fabrics coated with ZNO graphene, each concentration is 0.74 for Z1, 0.72 for Z2, and 0.70 for Z3. The decrease in the value of porosity indicates that the surface density of the fabric is increasing. The next is result. This result explain about absorption spectra of ZNO graphene with variation in concentration. These results show that the maximum excitation state is observed at 4 electron volt. The band gap of the samples Z1, Z2, and Z3 that show in the line green, blue, and purple. Absorption in the visible ring was also observed. This is presumably from the presence of defect in the system, such as the presence of oxygen vacancies. The next is wettability of ZNO graphene. The wettability of the fabric was analyzed by measuring the contact angle of the water droplets as these figures. And this figure shows that the concentration affect the contact angle and porosity. The higher concentration, the larger of particle, so the smaller the porosity. Of the various models proposed to predict the contact angle of water above the surface, the Wenzel model is the most effective because this model can define that the relationship between the contact angle and superhydrophobicity in a uniform composite surface and the observation obtained are that liquid droplets adhere to the fabric surface. This is an accordance with the result of XRD and SEM characterization. Summary: the cotton fabric with a superhydrophobic surface has been successfully produced by coating ZNO graphene. Synthesis of ZNO graphene composite on cotton cloth with various concentration was carried out using an easy and fast method using hydrothermal and spray coating. The result of the analysis showed that the crystal size and the contact angle of water are directly proportional to the increase in concentration. Our results show that the ZNO nanorod graphene composite has the potential as a superhydrophobic coating on the cotton fabrics to obtain the same properties as medical masks that can be used as reusable personal protective equipment. Thank you.
Okay, thank you for Diana Rahmawati. There are questions for Diana Rahmawati. Okay. For Diana Rahmawati, how long does the superhydrophobic coating last on cotton fabric until it's not reusable?
Thank you for the question. My experiment is I'm never no sorry sorry I'm so
How long the superhydrophobic coating lasts on cotton fabric until it's not reusable? How long? Maybe 1 month? 1 month?
there's no I don't research how long it's until not reusable because I just experimental until the superhydrophobic is issues.
Okay.
There's more there's more experimental again for it.
Okay, maybe in the future you can try to use until your material cannot reusable again. Okay, thank you for Diana Fatmawati. Okay, finally we come to the end of parallel session today. Tomorrow we have 3 pleno session. We invite all participants to join in pleno. We will give certificate to all participants who have joined in all session of second I-CoRE conference. Okay, thank you for your participation today and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam. To everyone within this room, you are allowed to leave. We will continue the conference tomorrow. Thank you.